Well, let me take you on a brief aerial tour of an area in Iceland where I do some of my research. I had a chance recently to take a flight in an ultralight plane over some of the lava flows that we've been studying recently. The ultralight plane, maybe you know it's sort of a cross between a hang glider and a motorcycle. So it's kind of an exciting and bumpy ride over these lava flows. These lava flows were erupted in 1984, so they're very, very young. And you can see the beautiful dark chocolate brown material spreading out across the horizon here. These lava flows erupted actually over a period of almost 9 years, and the youngest ones were erupted in 1984. We're near a place called the Krafla Central Volcano in Iceland. One of the reasons we like to study Iceland is that it's very similar to the terrain on the bottom of the ocean, near the mid-ocean ridge spreading axis, where lavas are erupted. In fact, where most of the lavas are erupted on our planet. So this is a wonderful analog for the bottom of the ocean and mid-ocean ridge spreading centers. As we fly over this area, you can see a very wide range of features. And let me try to describe some of those as we fly over them. I should say we're flying at it only a couple hundred feet up and really slowly, so we can get a really good look at the different lava flows. And one of the things I want to point out is that some of the small little lobes that are produced along these lava flows are the same size as what we see and what we make in the Syracuse Lava Project. So we're flying basically from north to south toward the middle of the Krafla volcano. So we're looking at the lavas that have flowed out toward us. The youngest ones are the darkest ones in general. And you can see that they overlie older lavas. The older ones you can see are green with vegetation, and they stand out very clearly in little hills that the lava has flowed around. Notice how the lava flows have just flowed around and emphasized the topography here. Sometimes the lava's flowed over those older hills and sometimes over younger hills that have been produced as little volcanic cones that were erupted at about the same time as the lavas were flowing. Most of the lava flowed out of what we call eruptive fissures. Those fissures are long, giant cracks in the earth, and you can spot them here. You'll see they're aligned small cones and craters that run across the terrain, more or less north-south. And there's some snow trapped down in some of them, so they're easy to spot. Notice how the lava flows have poured out of those fissures and spread out laterally east-west away from that and flowed around that topography. In a couple places you can see where the lava has even flowed down into giant cracks in the ground, that is fissures that have opened up as the earth's been pulled apart. Remember, we're in Iceland, a place that's just like the mid-ocean ridge where the earth's being pulled apart and the lavas are flowing out onto the surface. A couple things to look for is lighter colored cones that are standing up that the lava has flowed around. That's pyroclastic material that has been blown out of the volcanic fissures and kind of piled up to make little cones. Those cones are only less than about 50 meters high. They're not very big hills, and some of them have craters in the top of them where lava has poured out and then maybe even drained back into the earth. Other things you can see are some of those young lava flows are pahoehoe flows, that is the nice smooth type lavas that we make most of the time in our Syracuse Lava Project. But they transition into that is chunky, blocky, jagged lava flows toward the end as they flow. And you can see some streams of very dark lava that have spread out across the smoother pahoehoe lava flows. There are a few large smooth areas that have very distinctive polygonal fracture patterns in them. Sort of those fractures outline areas that are a few meters across, and about the size of a room, that are surrounded by these intersecting cracks. Those are lava lakes, or frozen lava lakes anyhow, places where the lava was sitting in a large pool and eventually probably drained out of those pools. And then as it cooled, it made those polygonal fractures. This is a good time for us to reflect upon what we've learned from the Syracuse Lava Project and how we can look at lava flows differently now that we've done these sorts of experiments. Some of the things that we've learned are how to make those different forms of Pahoehoe lavas, that is the smooth, channelized flows, broader flows that have that sort of elephant skin texture to them, and also lobate flows that are sort of lumpy and inflated in some ways. We can see all of those in the terrain down below us and see that they form in different types of places. You can see how the slopes have varied, and of course that's why we vary the slope in our experiments. And there are other places where there are sudden transitions that must have been caused by some other sort of process, some other influence, maybe because the rate of output of lava, that is the effusion rate, has changed. Anyhow, by looking at many of these small-scale lava features and how they integrate to make this very large flow field, you can see how we use our information from the Syracuse Lava Project to start to understand how large lava flow fields form.
When I initially got started with the lava, I had very concrete plans about where I was going with the project. The idea was to pour basketball court size lava flow. And I knew early on that the furnace we're currently using, the gas-fired furnace, I was using it to learn how to make lava and how to work with it. Then the coke-fired furnace, that would be the device that I would make the large lava flows with. I've learned a tremendous amount about an incredibly difficult material to work with. I should have known better when I did my research 4.5 years ago, and there was nothing on the internet. Not that the internet's the end-all of information, but there was no references. There's nothing. I've had to develop the knowledge over the last 4.5 years of a process. Now I'm really interested in, so that's changed. The idea of where the artwork was going has evolved in the last 4.5 years. And I'm very, very interested in pouring it inside, where it's just in a building from 1 to 3 months. We figured out how to do that. Now I just have to find a person crazy enough to allow me to do that. How I see it inside a building is similar in that it's poured in a steel form, like a low steel box that holds it, that when you walk into it as a viewer, you see this, you don't know how the lava got in there. The furnace is not there. There seems the origin, you can see where it flowed from, but you don't know where the lava really was generated, be it in the parking lot, being in that building with some monumentally huge air conditioner that is, taking the heat out of the space. But that's where I see the work going now. And that's what the last 6 months I've been focusing on. Everybody that's seen it, from the 4-year-old to the 94-year-old, have the same reaction to it, and that's pretty amazing. That's the one thing that's a truth.
Things that are major outcomes for me come in the major 3 components of the project. I mean, in the scientific part, I think it's really been a terrific refresher, a reminder to me about how much fun and interesting it is to do experiments and how fun science can be. From the sort of artistic perspective, of course, I've always really enjoyed the aesthetic parts of science, and especially geology, which is just full of wonderful images, but it just reinforces my attachment to that sort of aspect of the science. And educationally, as Bob said, it's one of the unexpected things was just the impact on people and how strongly people react to seeing lava and engaging in science and understanding how science and art can work together to inform one another.